Hello everyone. Let's talk about the last two topics in this unit, which are entropy and calorimetry. So let's start with entropy. Entropy is just the disorder or lack of order in the system, which means, and we decide that based on how the particles are arranged. So if the particles are close together, they are packed, they are very organized, there's less entropy. And if the particles are super far apart, they're just in random directions, like moving around, there's absolutely no order, then the entropy is very high. And so if we are given a question where we are looking at a physical change, which also includes the phase changes. So let's say we are going from a solid phase to a liquid phase, or liquid to gas, or gas to liquid, anything like that. And if you are asked that what happens to the entropy of the system after this change, remember that solids have very low entropy because they are very ordered. Gases have high entropy. So if we are looking at a phase change where we are going from solid to liquid, your entropy of the system is going to increase because we are going from something that has low entropy to something that has a little higher entropy. Comparatively, if let's say you're going back from a gas to a solid, your entropy of the system is going to decrease because you're going from something that has like a lot of disorder or very high entropy uh, to something that is very organized and has low entropy. And if you're looking at chemical changes, so which includes chemical reactions, there are two things that we can look at to determine the entropy of the system. First thing to remember is that compounds have low entropy compared to elements, and elements do include diatomic elements as well. So H2 is a diatomic element. Uh, and if you compare H2 with H2O, H2 is going to have a higher entropy compared to H2O. And that's because elements for the most part are free. Compounds, however, are bonded, like elements bonded together, so they are more organized. Um, and another thing that we can look at is if we have a big chemical equation, we compare the reactants and the products, the side of the equation that has more molecules. So let's say we are looking at a synthesis reaction, we have two reactants and they are combining to make one product. Your entropy of the reactants was higher. So now after the change, your entropy actually decreased. Comparatively, if we are looking at a decomposition reaction where we started from one reactant and we went to two products, now your entropy of the system increased because we have more products, more molecules in the products, so your products have a higher entropy. So that's how we determine the entropy of a system. Okay, so let's talk about calorimetry now. Calorimetry is in general just the study of the heat transfer from the system to the surroundings or from the surroundings to the system. So here we have a calorimeter. It's just a styrofoam cup because we are stopping any heat to go like escape the styrofoam cup when we make this calorimeter. So the system that we are looking at in this case, it does say in the picture is dissolved in water, but the example that we looked at in class there, we used a metal block. So that was our system. And then the surrounding is your water. So what we did was we heated up, we definitely took the mass of the metal block and we heated it up. And so our initial temperature technically for the metal was the same as the boiling point of water because we heated the metal until the water was boiling. So the initial temperature of metal was like 100 degrees Celsius. And so we put that in the water and then we just like closed the calorimeter and we waited for the metal to release its energy and the water to absorb that energy. So that is the exchange of heat energy that was happening. And what happens when heat is transferred is that it always goes from something that has a higher temperature to something that has a low temperature. That is a very common thing, and we all know that, but it's just something very important to make a note of. That heat always goes from higher temperature to lower temperature. So in calorimetry, ideally, And this also relates to the law of conservation of energy, which means your energy is neither created nor destroyed. It is just transferred from one thing to the other. So based on that law, whatever amount of heat energy is released by the metal is the same as the heat energy that is absorbed by the water. So the thing to remember here, however, is that the heat, when it's released, we are looking at an exothermic reaction. So your heat is going to have a negative charge. And this Q is actually the lowercase q, as we looked at in our heat equations, in Q equals mcat, and Q equals m and heat of fusion, and Q equals mass and heat of vaporization. So it's a lowercase q. And when the heat is absorbed by the water, that is an endothermic reaction now. So your Q, or heat, is going to be a positive number. So that is a super, super important thing to remember. And overall, that heat released by one thing is equal to the heat absorbed by the other thing. So let's verify that by looking at the numbers. So this is how we filled out our data table in the class notes. For water, we were able to get the mass. We already know the specific heat of water, and then we were able to get the initial and final temperature. For the metal block, we got the mass, we got the initial temperature, we got the final temperature, but we don't know the specific heat of the metal block yet. But we can figure that out. So we'll talk about that in a second. But before that, let's go ahead and calculate the amount of heat that was absorbed by the water, but using these conditions. So we have the mass, we have the specific, we have the specific heat, we have the change in temperature. We can go ahead and use the Q equals mcat equation, and then we plugged in the numbers and we got the heat energy for that was absorbed by water to be 3,112 joules. And then we looked at how can we use all of this information to calculate the specific heat of the metal. Now, ideally, we would want to use the Q equals mcat equation. The problem is, from that equation, we already have the mass and we do have the change in temperature. Specific heat is what we are calculating. But where do we get the Q from, the heat? So remember that in this calorimeter, and according to the law of conservation of energy, the heat that was released by the metal is the same as the heat that was absorbed by the system. So when you plug the heat that we already calculated for the water into the equation, your specific heat turns out to be negative 1.09. Now, specific heat cannot be a negative number. So what did we do wrong in that equation? Remember our discussion about the exothermic and endothermic reactions now? We said that yes, the numbers are the same for the heat absorbed and heat released, but the heat that is released is a negative number and the heat that is absorbed is a positive number. So when we are plugging in the 3,112 joules, that was a positive number because it was the heat absorbed by the water. When we plug that in for the metal, it's actually going to be a negative number. So your correct setup would be this, and that's how you get your specific heat to be 1.09 joules per gram Kelvin. All right, and that was it for the calorimetry and for this unit.